After they maybe we have it shock the bacterial, we can put this one into the ice box long enough, or like maybe either the time of cooling is too little, or we just took too long of time to put it into ice box.
Okay, field transformation. What else?
Accidentally spreading water.
Just wrong spreading. But remember, you need to think about something that worked for 3 groups. we have issue with the cell that was used to begin with, right? Either it's not competent or your cell died during the generation of competent cell, right? That means no matter how good you do the transformation, the cell died. You are spreading that cell, or the cell simply cannot take the plasmid. If they cannot take the plasmid, then they will not grow in LB ampicillin, right? Okay. In this case, how do you think we can test this theory?
Plastic grow.
Wait. Cheryl first? Oh no. You are raising your hand, no? Cheryl.
Just take the competent cells and then grow the competent cells in LB agar without any ampicillin.
Okay. That one can be solved, right? Grow on LB minus ampicillin. Right? What other theory can be tested with this approach among all of this?
Ampicillin too high.
Ampicillin too high. Okay. What else can we test it with this? Hmm? There's one more theory that we can test with using accidentally kill transform cells. That one. Yeah. What theory can you at least narrow out? If let's say they grow on LP minus ampicillin. From cell transformations. Right? If your cell grow in LB minus ampicillin, that means there's a chance it's actually a LB transformation. And then if let's say it grow whether the cell alive to begin with or not, right? Group 3, non-conform, nothing grow. Group 3, undiluted, nothing grow. Group 1, very small amount grow, but very small, right? Both of your sample grow. Each of you have two sample. Where is group 2 yet?
I think the only one quarter is the
Oh, this one is group 2.
Yeah.
Oh, okay. Group 2 nothing grow. Group 3 very small amount grow. You have 2, right? The other one nothing grow. And group 1 both grow. You can pass this around. Yeah, we pass some it, so it's okay. But just don't forget to spray your hand. It's all. So nothing, right? That's group 2. Okay, which means group 2 this possibly correct, right? Group 1 you end up asking cell from 2 here. Group 3. Okay, that's explain, right? Why group 3 and group 1 have very similar result. Which means group 2 your issue raised in making competent cell to begin with. But group 3 cell grow, which means that's not the only issue we have, right? Because if the competent cell is the only issue that we have, group 2 that will explain your lack of colonies, but that does not explain group 1 and group 3 lack of colonies. That means yes, we address one issue, but we have other issues, right? Following so far, everyone? Okay, so now we know that this is addressed. Now we need to find other way to test things, right? Okay, so this one is already proven completely, right? No more question asked. Solved for every single group. Now there is a chance of failed transformation, unprecedented concentration too high, and competent cell non-competent. How do you think we can test this? Still all three. Failed transformation, unprecedented concentration too high, competent cell non-competent.
For 6, review the ampicillin, but with more care.
Compared to me, what? We use the same concentration. Yes. So this one also no, because I did this already. We optimize it, and we actually repeat it again. Yes. Right. Okay. So this one solved. This one solved. Okay, what else can we do to check what go wrong?
Higher amount plasmid
Use higher amount of plasmid,
of different size of plasmid.
different size of plasmid. Again, plasmid size too big. Say with ampicillin, this is optimized in our setup. But if you are working properly later on for ED or your thesis, and you have no idea this plasmid work or not, as Peter said, you can either use different size plasmid or use different plasmid at the same time and see if it's still working or not, right? Or use any plasmid that you know for sure will work as your positive control to know whether the issue is in the technique or in the plasmid size itself or the ampicillin concentration, right? Yeah, Sarah, you want to say something? Yeah, sure.
Maybe like do another
different concentrations, right? That one is the best, this one. Okay? Use tested cells and then plus higher concentration plasmid. Right? But the issue, in order for us to do this, to use group 3 cell, we need to know that group 3 cell were to begin with. But we did it all together yesterday. But as Sarah mentioned, we use a tested cell. Remember I told you I make backup for everything, that I have double check everything. So I try to use all your plasmid, transform it again at the same concentration to my own content cells. Right? Let's see the result.
Miss Nancy.
Thank you.
Gojek. Then
Xbox.
Thank you.
now we need one.
Fluoridation and addition progress. The thing is, we use competent cell, my competent cell, group 2 empty, group 1 all empty, group 3 also all empty.
In that one, we use your competence
My competent cell,
with our plasmid competence.
yes. But this one, you know that, but this, as Vishal mentioned, there's just by competent cell also can be issue, or simply my transformation doesn't have issue, right? So what do you do?
Check with your plasmid.
Use my class. All for a group. So your group 2 have both issues. The cell issue and the plasmid issue. Group 1 and group 3, your cell seems fine. But at least you don't kill yourself through our transformation, because group 1 and group 3, I still can culture it in non-amphiphilic, right? That means maybe your transformation failed, but we know for sure that my transformation doesn't fail. This one actually Michelle did a head shock, right? And she did all together. So that means this is almost like a transformation control. If transformation is the issue, all plate will not grow. Right? The fact that some actually did grow means this time transformation is not the issue. Right? Not the spreading. So I did all the spreading, Michelle did all the head shock, and then we also test all my cells in this one. Yeah, this one is your transform cell. The one I already transformed, the one we already said that. This one is my competent cell within LB non-amphiphilic. And then you will see the amount of colony is different than group 1 and group 3. some gyms finish it. So we don't have enough for us to do higher concentrations. Okay. Let's discuss what we will do today. Okay, as usual, right? Let's go step by step. We'll start with Ari. Ari, what's the first thing we need to do today? Colony picking. Okay. So, why we need to do colony picking? What is the purpose of colony picking? What do you want to check? Listen. What are we checking today? Oh, so we are going to check the size of the plasmid. Okay, Rhea, what else? Why we need to do colony PCR?
So we're taking the colony of the bacteria, and then because we want to amplify it, but we actually want to amplify the plasmid, we want to make sure that the bacteria will be in and we will identify it as a parasitic antigen.
Okay, in that case, if they don't take the plasmid, they will not grow in alveoli. So why we need to do colony PCR again? Carol.
We're doing colony PCR so that we can validate whether our insect is already inside of the recombinant cells.
Okay, Steffi, how can a colony PCR tell us if our plasmid that we have in our cells contain our insert or not?
So because the primers that we use target the specific sequence that we want, which is like around 200 pp the insert size. So later on, after we amplify that specific sequence, only we can know like whether the colony have the correct insert that we want.
Okay, that's very close, but remember what is the size of our insert data? 228. 24 base pair. Right? How can you do a PCR to check the presence of 24 base pair insert when the primer itself, in average, what's the size of average primer? Peter? 28. So how can you check the presence of insert and run PCR if your insert is only around 24 base pair and primer size is already 20? You cannot even fit a forward and reverse primer in your insert. What should you do?
Fit one plasmid targeting the insert and one plasmid targeting the outside.
Plasmid?
Oh, primer. One primer targeting the plasmid area. Because if only one in the plasmid regions is have the plasmid attached, the exponential PCR will not happen. So it will not give any result.
Everyone understand what Victor mentioned?
They need two attachment.
Okay. Let's draw.
Let's draw.
So we try to explain the sequence only.
Do you have other than that? Okay. Okay. So we have a plasmid, right? And method of replication, and so on. Right? So, what we do PCR. But how can we do PCR? Simple. This one is double strand and match. We'll just use the oligo here as reverse primer. Exactly this oligo. Because this oligo will completely complement with this oligo. Following? Every reverse primer requires forward primer. So reverse primer go here. You make one more primer targeting this area like this. That means if you don't have any insert, forward primer can attach. But reverse primer, this is our oligo. It only complement with oligo, right? So if your inserts are not there, your forward primer doesn't have the pair. So it cannot create any sort of product. Following? So the product only can be made if the insert is there. Yeah? Yeah?
I'm very confused about saying that there is no product because when there is the forward primer, because plastic is like
Circle.
then it can like just go. There's no.
Yes. But remember the size of our plastic? It's not sustainable. Our PCR, that's why when we learn about PCR, what is the optimum size that our PCR can PCR? 600 HPC. More than that is almost unPCRable or it's not stable.
Is there anything you need to concentrate on what exactly the forward primer should be?
Forward primer should be technically if you just like any other primer design, right? You need to make sure that your forward primer can only attach here. If the sequence that you choose for forward primer also available here, here, and here, it will be very difficult, right? And then the size. And then as usual, you see sequence, right? Annealing temperature, and since we are using this fixed reverse primer, you cannot switch it, right? Because it's a very short base. You cannot have time to decide the sort of other primer. You need to match the annealing temperature following this. As you know, forward and reverse cannot be more than 5 degree differences. As close as possible. General primer rule, no hairpin. Yes, in general primer rule. Following? Okay. The issue is, yeah, shall we go back? If the button is here, both attach, right? So when we do apply not grow because they pick up the colony, the plasmid, but because they develop resistance. Okay, and there's one more reason why we need to do colony PCR. Mutations. Yes, the plasmid itself, as the cell amplifier, they amplify the plasmid, right? The sequence might change. The plasmid itself, as the bacteria start to amplify, right? There's a chance their plasmid already mutated. Technically, we don't care too much as long as the mutation does not happen in the intestine or the insert area. But unfortunately, in the intestine, we cannot really test that, right? Because the intestine is big. Even if we do like PCR, we don't know exactly where it mutates, right? So if, as long as the mutation doesn't happen in the 5' or 3' primer still get touched, they will amplify the mutation anyway. However, if the mutation happens in this insert area, we can test it because if mutation happens in this insert area, the primer will not attach. It will not create product. So that's why even though you know for sure your plasmid enter, every time you do transformation, you still need to do colony PCR. But as Sarah also mentioned, you think one colony is positive, you cannot assume the other colony in the same plate is positive as well. Means the one that you do colony PCR need to be the exact same colony that you amplify with. So how we do that? How can we do colony PCR and still amplify it? And it's only a very, very small colony. Share it.
We put it in, we dilute the colony into water, take a small amount from the PCR, like 1 microgram, then the rest put it into the aluminum to go deeper.
Yeah. Why it need to be water, Priscilla? Why cannot we just pick colony and put it in group, let's say?
We still want to dilute it, so it's not to
Why don't we dilute it in albumin? Isn't it healthier for the bacteria? Because we want bacteria to be alive to begin with. Why don't we just amplify it in albumin? Put the body, put it in albumin, use the small amount for PCR, use the small amount for amplifications. Guess it's okay. If you don't know, just try to guess. Based on things that we have learned so far, like last week I told sometimes when we do elution, we need to sometimes use the E buffer, sometimes use NFW, right? There's a concentration that goes behind it. The concentration while we use water is very similar to zero. Just think about it. What's the benefit of water as compared to albumin? Okay, but water doesn't contain too much nutrient for the bacteria, but we actually want this bacteria. Joy, do you have any? Bree first. Bree, what else do you think can possibly explain the choice of NFW?
without having too much cells.
Okay, without having too much cell. Is having too much cell a bad thing? So,
So that we can have a more
control amount. Okay, anyone else? Joy?
quite similar with brains because we just want to have more, have lesser bacteria. We don't want to.
When we do PCR, the more sample we have, this is not your PCR, this is PCR, so we are not doing quantitative. The more sample you have is a good thing or a bad thing? Good thing, right? qPCR sometimes is too much, is make false positive, you cannot really compare because they get threshold too fast. But normal PCR, the more sample you use, the thicker the result you see in electrophoresis, right? Monique, can you think of anything else that time, what should we do to prevent the bacteria in the water to die? Ice. And we need to put it in the laboratory on the same day. Right? We can usually sometimes we do PCR and then we keep the result. We run the electrophoresis a bit later, right? Maybe the next day it's fine. But now this time no, because you are working on ticking. Time is fleeting for us, right? And usually when we do PCR, we don't really need to make sure sterility. But this time we do because we don't want the water to be contaminated with something else. When you make the master mix, sure, it doesn't have to be sterile. But if you are going to use the same tip box to touch the bacteria later on, it needs to be sterile. Because you don't want to introduce any sort of other bacteria or contaminant to your water solution. Following? Everything clear for today? So that's what we get. But the water that we use to dilute is the one. So we literally put. So this is already water, and we need to only put, right? So each group need to pick 5 colony at least, 4 to 5 colony. So I have 4 plates here. Yeah. So I have 4 plates. Why don't each group pick 4 to 5 colonies? So 1 colony from each. Yeah. All quite a lot of colonies. Yeah, you pick 4 to 5 colony, right? So you have aliput. How many you should aliput? How many water put? 10. And in the tube will be somewhere along that line, right? And then colony A, B, C, D. Need to be done aseptically, 100% aseptic. Alright? And then you make master mix, PCR. Right? And then you aliput the master mix each. And then you take how many microliter? 2. So you have 8 microliter left. This 8 microliter you put on ice. Right? As we run this PCR. We make this PCR, and then as we make this PCR, then you need to already prepare the gel. Because we need to work fast. Because the moment you take the colony out to the water, your clock already started. Right? Bacteria in general quite strong, but it's not that strong. Right? So once it's run, we run electrophoresis. After the PCR finish, we will run electrophoresis. After run electrophoresis, gel dock. And only the one that have the result, exactly the size that we want, we will already prepare healthy product. No, not the PCR, because PCR denaturate, right? Usually for mammalian, you need to lysis the mammalian cell first. But for bacteria, because bacteria is small, the first step of PCR is denaturation. Denaturation, the heat by its own will already lyse the bacteria. So we don't need to have additional lysis step. That usually we need to do with normal mammalian cells. With bacteria, we can literally put the bacteria as is with all the plasmid in it, still alive, put it in PCR, mix with the other. As they denaturate, they will denaturate the cells, they will denaturate the plasmid. But just in general, when we do the pre-denaturation, I like to do it a bit longer, the pre-denaturation cell. Because they need to quote-unquote lyse the cell first, then they can have access into seed cell. Yeah, you guys are already not CCP student, right? Okay, group 2. Reta. Reta did the most of culture, right? I think. How many projects you do? Three, yeah? Okay. Three, zero. Okay. So you guys are doing some culture and then making gel. Who want to volunteer making gel? Okay. Have you made gel before? Okay, sama saya. Who want to make gel? Who have the least experience making gel? Okay, Jason. Anyone want to accompany Jason? Okay, Peter, yeah. The last time that made gel is Reta and Ria. Okay, now Peter and Jason, yeah. Okay, so you two later on make gel. And we have 4 plates. Each group is a plate bacteria, right? So between the 3 groups, you guys just circle around the plate. Now let's say group 1 take plasmid from this plate, and then group 2 take from this plate, and then after that you guys do pick. Yes. So this 4 plate is shared between the 3 groups. So what are these 4 plates? Same with you guys. I did the 1 to 12.5 ratio and 1 to 25 ratio, right? So and actually they're not being totally different plasmids. So Michelle yesterday take 2 plasmid of myself. I have 7 backup plasmid by the way. Yeah. I made 50 tube for competence of backup. Because you make 1 tube and you make 50 tube, the effort is the same. It's just the volume is different, right? It's better for me just make bulk. It's been used for heating. Actually, it's been used for your skin. I don't know, right? So each group needs to have, and then the 4% is non-diluted versus tenfold dilution. Right? So usually non-diluted will always have higher number of colonies because it's non-diluted. But because this is also higher number, the concentration of bacteria is high. Actually, the chance of the bacterial mutation, they got comfortable and then they let out the plasmid is a bit higher in non-diluted as well. The dilution, the concentration is very low, right? Usually. So if they grow, the chance of it containing the right plasmid is a bit higher. So that's why I want you guys to actually test all 4. Yes. And this.
So for 12.5 to 25 and then the diluted and non-diluted.
Yes. So you have 12.5 non-diluted, 12.5 diluted, 25 non-diluted, 25 diluted, and NDC for per group. So 5. Following 5 PCR per group. Which means you require 20 well in agarose electrophoresis. 15. No, 16, right? So yeah, usually you 20, right? 20 Everyone get what?
It's the whole letter.
It's still enough. Your sample is 17 plus letter. Everyone letter is 18, right? If they use 20, well, the most already.
Use type
Okay,
1.
everyone clear in what they need to do, yeah?
So this is our plan.
Something, yeah?
We want to make 60.
Yeah. So, yeah.
Oh, for one gel, I think tomorrow and yesterday is 60.
And you guys also need to be clear, yeah, when you pick column A, the A, B, C, D, put in your notebook to know A, B, C, D come from which plate. For example, A is 12.5, or non-diluted, or something like that. Give yourself a code. I think it's easier for the three groups decided what the code of each plate would be. Yeah?
Yesterday is about 60 and now just like maybe we take 60.
What time is it?
Nothing down first. Yeah, let's label.